right, well, hopefully you did well on your quiz just now. Go and take out your notes if you would, please, and let's begin reviewing in earnest for the exam. Again, technically, yesterday as we worked on systems of equations, yes, we were preparing for today's quiz, but we were also preparing for the exam, and a large part of the exam will involve systems of equations. The work problems you did for homework last night, that was preparation for the exam. The one thing really with systems that weren't reviewed yesterday and weren't reviewed on the homework were some of the terminology, which some of us remember from a few quizzes ago, is pain. You want to make sure you know your terms. For instance, system of equations and the graphs intersect. We call this a consistent system. You will want to write that in your notes again and make sure you memorize it. If they intersect, it's consistent. If they don't intersect, then this system would be called, class? Inconsistent. And what's the answer? No solution. Now, if you're dealing with linear equations, they didn't hear that on YouTube, it's okay. If you're dealing with linear equations, it's possible you could have one line and another line, where the lines are coincident. Now, technically, they do intersect, don't they? Technically, it's consistent, but we refer to the individual equations, since they're the same thing, we call the equations dependent equations. Think of it this way. Some of you are to the point now where you're driving yourself and you need to go somewhere, whatever, you can do that. Many of you are not. Many of you, where mom goes, you go, whether you want to or not, because you're dependent still. Where the first line goes, the second line goes. Those two equations are dependent. Does that make sense? And the answer here is going to be indeterminate, because there's just too many answers. By the way, indeterminate is also how we describe a single equation, right? Because just as this has an infinite number of solutions, so a single equation presents an infinite number of possible solutions, right? And remember, it's these indeterminate solutions where we would use the parameter to specify our answers. Make sure you know those terms. It'd be a shame, wouldn't it, to get all the work perfect on the math and then miss just the terms and not get that 100, not get that sticker. Wouldn't that be awful? You don't want that to happen to you, so make sure you know your terms. All right, that wraps up systems, though. Okay, so we've spent plenty of time. We've spent plenty of time working on that. I gotta pick on you sometimes, okay? I pick on everybody else. Let's go and review some things, going all the way back now to Chapter 4. If you want to jot this down, the exam does cover sections 4.1 to 5.4. Sections 4.1 to 5.4. Chapter 5 is the systems. All things systems, and I'll be honest, I didn't use the book a whole lot. You might have noticed a lot of handouts, a lot of my own notes. So, use the book however much you want to with that. But Chapter 4, we did use the book considerably for. Chapter 4 was all things graphing. We first got started, right? So, for instance, introduced you to the idea of these number lines that intersect. We call these number lines, class, axes. And, of course, we put arrowheads at the ends of the axes to show that this number line goes to infinity and beyond, to negative infinity, and up to infinity, and down to negative infinity. And this number line, this axis, specifically, class, is called the x-axis. Now, class, is this vertical or horizontal? Horizontal. It's horizontal. This is vertical. Vertical jump is not how far into the wall you can jump. It's how high up you can jump. Okay? And the y-axis is the vertical axis. This point where the axes intersect is called the origin. It's the origin of each number line. It's also the origin of this thing on which we graph. We call this thing the Cartesian plane. A lot of terms, by the way. These four sections you see here are called quadrants, where this quadrant here is quadrant 2. This is quadrant 1, quadrant 4, and quadrant 3. Right? Every point on here has a specific x value and has a specific y value. Well, the x value of any point, class, is called the of a point. The x value is called the abscissa. Abscissa. A-B-S-I-S-C. S-C-I-S-S-A. Spelling's not much stronger. Spelled abscissa, but with a silent C. Abscissa. And then the y value class is called the ordinate. The ordinate. Again, that's not ordinate. I've seen that before. It's ordinate, but it's ordinate is how it's pronounced. You put this abscissa and the ordinate together, class, and suddenly we have the point's exact location called the coordinates. The coordinates of the point. Off? Cough.
C, remember?
Huh?
Never mind.
And then cough without C. Off.
I don't remember. We have the point's coordinates. I don't know what they're talking about. I'm sure it's funny and I want to laugh, but I don't know what they're talking about. All right, the abscissa and the ordinate coordinates. Now, if I were to graph... Anyway, if I were to graph an equation, any equation that produces a straight line class is called a linear equation. Good. How can I spot a linear equation?
Straight line.
X and Y are both to the first power. So something like this, for instance, would be a linear equation. It probably doesn't look like this, but it'd be a linear equation. It'd be a straight line. Where any graph, including, for instance, that parabola we talked about, any time a graph crosses an axis, these points where it crosses an axis are called intercepts. These 2 points would be x-intercepts. This would be a y-intercept, right? Y-intercept, x-intercept, right? Intercepts are where the graph crosses, or where a graph crosses the axes. Now, for our linear equations, we said the ideal way to graph them is to get them into a specific form called slope-intercept form. What is slope-intercept form of an equation, class? Y equals mx plus b. The key to slope-intercept form is to get the y by itself. The coefficient of the x is represented by m. Of course, that's the slope. What is slope anyway? Rise over run, right? So we said that a line that, well, for instance, goes like this would have what kind of slope? Positive slope. A line that goes like this would have negative slope. So up and to the right would be positive, up and to the left would be negative slope. What about a perfectly horizontal line? Zero slope. It doesn't have slope, right? Zero slope. And a perfectly vertical line would have undefined slope. And then this b. What is the b right here? The y-intercept. So remember, if you happen to have something like, I don't know, y equals negative 3/7 x plus 1, well, you would start, in order to graph that line, class, you'd start at the 1. It's the y-intercept, right? And from there you would rise 3 and run backward 7, something like that. So you get a line that looks something like that if we were to graph it. One of the other things we talked about with graphing was if I gave you just 2 points on the Cartesian plane, this point and this point. Well, if I were to join the points by a straight line, I'd get something called a line segment technically, but I could find the length of that line segment. Well, the length of a line segment is defined as the distance between 2 points. We have a formula to find distance between 2 points. Suddenly people start panicking. What is the formula to find distance between 2 points? Volunteer. You all should be panicking. Write this down in your review notes. The square root of x2 minus x1 squared plus y2 minus y1 squared. Go and write that down and we'll say it together. Make sure we remember it for Friday. Lesson 134. D equals the square root of x2 minus x1 squared plus y2 minus y1 squared. Say it with me, class. D equals the square root of x2 minus x1 squared plus y2 minus y1 squared. And remember I said you can kind of get away with, if you went out of order somehow, as long as you're subtracting, you can get away with going out of order because the squared is going to reconcile everything. Positive, negative, u squared doesn't matter. However, we also had an equation to find slope, this rise over run. And on the slope equation, the order very much matters. What's the slope formula, Brandon?
y2 minus y1 over x2 minus x1.
Now remember here we said whichever y value you pick to be your y2, its corresponding x value had better be the one you start with in the bottom. Focusing up here, maybe writing that down if you need to. Also, make sure you put the y's over the x's. I saw it several times. I accidentally put the x's over the y's, and you know better. Don't mess that up. We have another equation, finding the point that is in the middle of a line segment. We call it the midpoint. What's the formula to find the midpoint of a line? Audrey, do you remember?
x1 plus over 2. And then y1 plus y2 over 2.
There we go. Of course, it'll be in parentheses because it's a set of coordinates. It's the coordinates of the midpoint. Remember, you're going to average the x's and y, so add and divide by 2. The hard part about that is you're used to subtracting, and suddenly now you're asked to add. Make sure you have these formulas, either in your notes or write a reference to go back and memorize that. With lines, we said 2 lines generally. It's kind of shown here with this dashed line. I'll kind of go over again. Normally, if I just draw 2 lines at random, they're going to intersect somewhere. It is possible, though, for me to draw a couple of lines that would never intersect. We would describe these lines, class, as being parallel. What is it that would make 2 lines on the Cartesian plane parallel? Genesis? If they have the same slope. So parallel lines, you need to remember, have the same slope. For instance, if I had this equation y equals negative 3 sevenths x plus 1, a parallel line would be y equals negative 3 sevenths x plus 5, sure. Doesn't really matter what you put right here, right? What'd you say? Okay, I was like, man, they both did that, yeah. They have the same slope, parallel. It's also possible that this other line, of course it just happens to intersect, but if I got a line that intersected perfectly at a right angle, this line is special. It doesn't just intersect, it intersects in a special way to form a right angle. We would describe this line, class, as being perpendicular. How would a line be perpendicular to another on the Cartesian plane? Maddie? Negative reciprocal slope. So that, for instance, if these 2 lines have a slope of negative 3 sevenths, a perpendicular line, class, would have what slope? Positive 7/3, right? So a positive 7/3 x, I don't know, minus 2. I don't care, right? But the negative reciprocal slope would be perpendicular. Questions on parallel perpendicular. All this coming back to us now from back in January. All right, turn your textbooks to page 319. Let's practice with this a little, shall we? Page 319. I want you to do pages 319 to 320, numbers 1, 2, 6, 8, 10, 12, and 13. They're at the bottom of page 319. You see where it says chapter 4. We're going to start there with the numbers 1, 2, 6, and 8. Turn the page 10, 12, 13. Take a few minutes to review over this initial graphing stuff that we did.
Are we graphing number 10?
Does it say to graph number 10?
Yes.
Look at that again. Yes, please do. Yeah, and you can do a quick sketch graph, though, if you want to. I don't need you to take time to get out graph paper. Just like I do on the chalkboard, throw it up there, make it look pretty close, so I know if you were doing it on graph paper for the exam, you'd have it. I don't want to spend a lot of time on it. By the way, tomorrow you will want graph paper, because we'll be reviewing over those parabolas and stuff, and that's really hard to do without actual graph paper. But today, no.
sorry.
That's neat.
Checking your answers to 6, 8, and 10 very quickly. Take just a moment. Check your answers to 6, 8, and 10. By the way, real quick, number 1, what kind of slope class?
0.
And number 2?
Negative.
Yeah, 0 and negative. The answers to 1 and 2 should have been really easy there. 6, 8, 10. How many perfect on all 3? Graph looks very similar. Answers for 6, 8, and 10 correct otherwise? Questions 6, 8, 10. Questions on 6, 8, or 10. Let's take a look at number 12 together. They want you to find the slope-intercept form of a line if you're given 2 points. Well, to find slope-intercept form, one of the first things you have to find, class, is the slope. So we should have found the slope, the y2 minus y1 over x2 minus x1. I'm going to start with the 9 minus the 4 with my y. So I have to start with a 3 minus an 8. That's going to give me a 5 over negative 5. Should have had a slope of negative 1. How many had negative 1 for your slope on number 12? Any questions on finding the slope?
I just haven't got there yet.
Okay, does it make sense? We remember how to, okay. So then from there, if I want y equals mx plus b, I've got one of my key components. I've got the slope. Class, what I'm missing is the y-intercept. What do I have to do to find that y-intercept, Michael?
You have to plug it in.
Plug what
X
in?
and Y. You have to plug in X and Y.
Good, plug in an x value and a y value. Well, which x value did you pick?
9.
Well, that's a y value, but
3.
3 for an x value, and the corresponding y value, of course, is
9.
9, and we know the slope now, so we can plug that in as well. That way, all we're missing is the b. We end up getting a b value or a y-intercept of
12.
12. So now that I know both m and b, I know my equation. What is it, Michael?
Y equals negative 1x plus 12.
There we go. You could put a 1 here. You could put a 1 over 1 here. In fact, if you were graphing it, we were graphing it. There's our equation. How many had that? Again, questions.
For number 13?
For number 12.
Oh,
We're about to get to number 13.
okay.
Question on 12?
I
All right.
got that.
So let's take a look at number 13. Abby's lucky number. And let's see how she did, how we did on that. We wanted the line that's parallel to y equals negative 3x plus 4 and goes through the point 2, 1. Well, Abby, if it's parallel, whenever I see the word parallel, I should be thinking
Same slope.
same slope. Well, what is the slope of the given line?
Negative 3.
So therefore, my slope is,
Negative 3.
and if it goes through the point 2, 1, we're kind of doing what we just did. We're going to have the y equals mx plus b, and we're going to plug in for the y,
1.
in for the m,
Negative 3.
in for the x,
2.
plus the b, and we end up getting a b value of
7.
7. So again, if you know the m and the b, you know the equation. It should have been.
Y equals negative 3x plus 7.
There we go. And how many had that for number 13? All right. Again, didn't get that far, but it makes sense. All right. The next thing that we talked about in chapter 4, we talked about variation, direct and inverse variation. That will not be on the exam. You'll cover that kind of thing a lot more in your science classes, chemistry and physics and things like that. So I'm not going to touch on that in the exam. We talked about functions. Remember we said a function is an equation for which if you plug in one value, class, you get out one value. Plug in 1, get out 1. There were a couple ways, 3 ways actually, to tell whether or not something was a function. One of them was called the vertical line test, remember. And in fact, I addressed this just the other day. We were looking at some graphs on the screen of some different quadratics. And we looked at this sideways parabola, and I said, this is a quadratic. It's just not a quadratic function because it fails the vertical line test. A single x value has 2 different y values, right? But the normal parabola, well, that's a function, has a vertical line. A single x only has a single y to go with it, right? So vertical line test was one way. We also had, if you had a list of points, right, you could check and see, does an x value ever repeat with differing y values? The final way, remember, was to actually solve the equation. And if you ended up getting a positive negative, then that would say, well, 1x would produce 2 y's, so we don't have a function. Do you remember talking about that? Whether or not something's a function. So for instance, looking at 15 and 16, right there on the page. Would 15 be a function class? Yes. And 16? No. Okay, so vertical line test, we're good? All right, from there we talked about two aspects to a function. And we said, since we've established that in any function, you plug in 1, you get out 1, right? That doesn't mean you can plug in whatever you want. There's actually only a certain set of values you're allowed to plug in for x. What term refers to all the values you're allowed to plug into a function for x? The domain. Make sure you have that in your notes if you didn't remember it. The domain is all of your x values that you enter. All of the x values that you enter into the function. And as we enter all these values, there's a lot of different numbers you could get out, depending on what you plug in, right? Plug in different numbers, get out different numbers. But you can't necessarily get out anything. There's oftentimes a set of values you're allowed to get out of a function. What do we call the f of x values you can obtain from a function class? It's called the range. The range. And again, I want to jot this down. Those are your f of x values, and those are what you obtain from the function. We had different types of functions, and their domains and ranges we memorized. We had, for instance, a constant function, like f of x equals 2. What's the domain of a constant function? Oh, really, you can plug anything you want in for x, considering there's not an x there, right? You plug anything you want for something that doesn't exist. What do you get out? Always get out 2. So the domain, remember, we said would be all real numbers, but the range would be, well, from 2 to 2, just 2. That's the only number you'll ever get out of it. We also had absolute value functions, something like f of x equals the absolute value of, I don't know, x minus 3 plus 2 or something like that. I don't remember. We had something like that. And we said the domain for an absolute value function. Well, what can I plug in? Whatever you want, anything you want, doesn't matter. You take the absolute value of it. But what does absolute value do to whatever we plug in? Turns it into a positive. So this right here can only be positive. How do we define positive numbers? Picture a number line. 0 to infinity, right? Those are your positive numbers from 0 to infinity. But then we add 2. So what is the range of the function class? 2 to infinity. What if, though, there had been a negative right here? Then all of a sudden, this absolute value actually only spits out negatives. How do I just define negative numbers? Negative infinity to 0, right? But then I add 2 to that. Negative infinity to 2. Do we remember doing this? Questions? All right. Another type of function that we had looked at was a quadratic function. Of course, we spent a long time on quadratic functions. It was something like an x squared, I don't know, be careful here, plus 4x minus 7. Doing some quick shady math in my head, and let's say the vertex of this has to be at -2, -11, hypothetically. I think that's where it would be. My math may be wrong. Gavin, I don't need a smart aleck to pause the video and work it out. Okay, let's just assume I'm right, that the vertex is at -2, 11. What's the domain of all the x's I can plug into a quadratic function class? All the numbers, plug in anything you want. But because a quadratic function is in the shape of a parabola, the range or the f of x or y values are going to go from this vertex point upward, correct? So, what's the range? Is correct. Right, -11 to infinity. Right, now, if there had been a negative in front of this, what does that do to the whole parabola? flips it down. By the way, it would also change my vertex. It wouldn't be this anymore. But hypothetically, if that were still the vertex, then the parabola goes down from there. So now what would the range be? Negative infinity up to the negative 11, up to the f of x value of the vertex. Okay, questions on that? We'd also looked at radicals, even roots specifically, something like f of x equals the square root of x plus 3 minus 1. And we said the domain, all the things we can plug in, not all real numbers, because the radicand class must be positive. It must be greater than or equal to 0. Well, what kind of number, give me an example, would give me something smaller than a 0? Negative 4 would be a problem, wouldn't it? So would negative 5, negative 6. The smallest number, in fact, I'm allowed to plug in is going to be negative 3. Anything bigger, I'm fine. So we would say that the domain here was negative 3 to infinity. Do you remember working that? And then as far as the range, well, this radical right here is only going to spit out what kind of numbers? Positives. Again, positives meaning 0 to infinity. And then I subtract 1. Negative 1 to infinity. Again, had there been a negative here, now this only spits out negative values, or negative infinity to 0. And then I subtract 1, negative infinity to negative 1. To remember radical functions, specifically even roots. The last type was one that we did study as well in a lot more depth, and we'll look at this a little bit more tomorrow as well, but those were the rational functions. Something like f of x is equal to 2x plus 7 over 4x minus 3. And we said here, the domain and range are largely all real numbers. I can't draw the all real number symbol, except there were going to be specific values that were excluded. Do you remember why? What appears in the graph of a rational function that causes exclusions? Remember? Asymptotes. Remember the asymptotes that cause there to be this kind of hyperbolic shape to the rational function. So we said the domain. I can have anything for my range, for my domain, except 3/4. X cannot equal 3/4 because the denominator cannot equal 0. You may want to put that in your notes. That's the one restriction on the domain, is your denominator can't be 0. If we had matching degrees of x in my numerator and denominator, we said that the range would be everything except 1/2 the ratio of the leading coefficients. Just can't equal the ratio, if you will. And again, that's technically if they're matching degrees. Remember, if the numerator is bigger, then it might be a slant, or you might have none. If the denominator is bigger, then it's going to be just the x-axis, f of x can't be 0. But those were our limitations on the domain and range. Questions on those? All right. For homework this evening, I want you to quickly list out some domains and ranges on 17 through 22, page 320. Page 320, numbers 17 to 22. You're given 6 functions. For each one, list the domain, list the range. Kind of like I just showed here. A chance for you to do it yourself. By the way, remember, if it's not one of these 5, and I erased a couple of them, if it's not one of those 5 special types of functions, it's just all real for both, right? But if it's one of those special ones, thinking those through, tomorrow we're going to review over function combination. We're going to review over function composition. We're going to review over quadratic and rational functions and their graphs. That's all coming up tomorrow as we wrap up this review for your third quarter exam. Exam again, lesson 134 over sections 4.1 to 5.4. All right, have a wonderful rest of your day. When the bell rings, you'll be dismissed.